So 6 is tangent of 195. And the directions on this ask us to use the sum or difference formulas. There's a couple of different options we could use here, but since it tells us what to do, we're going to do that. So I need to write this as a sum or a difference. I think I'm going to do 135 plus 60. There's lots of different...
We can't see your screen. It's not shared.
Thank you. Thank you very much. That's better than yes. Okay. So, again, there's lots of different ones you could do for 195. I chose to do 135 plus 60. So using the tangent formula then, I'm going to have tan of 135 plus tangent of 60 divided by 1 minus tangent of 135 times tangent of 60. So if I go to my unit circle, I can look up tangent of 135 as y over x. So that's root 2 over 2 divided by negative root 2 over 2, so that's just going to be negative 1. And then if I go to my unit circle, I can look up tangent of 60, which is, again, y over x, so it's root 3 over 2 divided by a half, which is just root 3. And then negative 1, and then root 3 here. So that gives me this. Gracie, are you okay so far to here?
Yeah.
Okay.
I think I got the part before that wrong, though. Like, I think I checked it wrong in the unit circle.
Yeah. That would make life a little bit more difficult, but still, you know, at least in terms of getting the answer that's in the back of the book or whatever. Well, this is an even one, so I guess that answer's not even there. But we don't like to leave our answer with a square root in the denominator. So to rationalize this denominator, since it has a sum in it, we can't just multiply the top and bottom by square root of 3 because it'll distribute to the 1 and I'll still have a square root down there. So what we do is we multiply the top and bottom by the conjugate, which is the same thing as the denominator but with the opposite sign in between.
Wait, Mr. Bullock?
Yeah.
Why wouldn't it be a 2 plus 3 in the denominator?
Because you multiply before you add. Because you multiply before you add.
Thank you.
You're welcome. It's 7:45, so no worries on that. So we'll FOIL this out now. So I have negative 1 plus root 3 plus root 3 minus 3. And the denominator I have 1 minus root 3 plus root 3 minus 3. So that's negative 4 plus 2 root 3 over negative 2. And then if I reduce that, I have 2 minus root 3. There's my final answer. Gracie, are you okay with what we did there?
Yes, thank you.
Of course. I think, Haley, you said you wanted to do 12?
Yes, thank you.
Yeah, no problem. So we have, this says to write it as a single trig function, so I have tangent 4 beta minus tangent 3 beta divided by 1 plus tangent beta times tangent 3 beta. So I just need to go back and look at my identities to see which one this matches up with. And if I look, this is the one that I'd want, is the difference of tangents, or difference of two angles for tangent. So my u is like 4b, and my v is like 3b. So the answer then is tangent of 4b minus 3b, or just tangent of b. Does that feel okay, Haley?
Yes, thank you.
You're welcome. Okay. Any other questions here? I'm happy to do a little bit more, but if you guys are happy, I'm happy too, so there's no pressure or anything.
Can you do number 13?
13? Sure. So this you'll recognize as one of the cofunction identities, or basically a cofunction identity from the previous chapter. But we're going to do this as a difference using the angle difference for sine. So if I go and just want to double check to make sure I don't screw up the formula there. So that's going to be sine of u times cosine of v, and then minus sine of v times cosine of u. If I go to my unit circle, I want to find the cosine of pi over 2. That's going to be the x-coordinate at pi over 2, which is 0. If I go to my unit circle and I want to find the sine of pi over 2, that's the y-coordinate at pi over 2, which is just 1. So 0 minus cosine of x, or just negative cosine of x. And I'm done. Is that okay?
Yes.
Okay. Sure. All right. So today then, we'll start by continuing in chapter 6, talking about half-angle identities. So I'll derive the first of these half-angle identities, but after that they're basically all the same. So the trick here is, to do the derivation quickly, is to start with your power-reducing identity. And then we're going to make a substitution. So I'm going to say let x equal u over 2. And I know that here that the 2's will reduce. And then I can just square root both sides of the equation to get rid of the squared. So that's our first half-angle identity. I'm just going to write down the other 2 now without deriving them because the derivation is basically identical. So cosine, there's just one version. Tangent, though, is a little bit weird because there's 3 different versions that we could use. Again, each of the 3 versions is going to give you the same result. So you are free to kind of choose which one seems to be the most convenient. So these are our 3 half-angle identities. And you'll notice in these 3 half-angle identities that some of them include a plus or minus. Now that doesn't mean you're getting 2 answers, but it does mean you need to make a decision about whether you should be getting a positive answer or a negative answer. And we'll show you how to make that decision here when we do a couple of examples. So let's do a couple of these, finding the exact value. And I'm going to use the half-angle identities to do this, just so that we can kind of get some practice using those. So cosine of 75, well, 75 is half of 150. And then if I apply the cosine formula, it's plus or minus 1, or the square root of 1 plus cosine of 150 over 2. And before I go forward here, let's make a decision about whether I should be using the plus or the minus. And the original statement here is what's going to tell me. So 75 degrees is in quadrant 1. So cosine should be positive in quadrant 1. So I know that I'm going to be getting the positive version of this plus or minus answer. So I'm just going to use the original statement and look at what quadrant the angle is in, and use what I know about sine, cosine, tangent, etc. to decide whether the answer should be positive or negative for that quadrant. Okay. So I'll go to my unit circle now, and I'll look up what cosine of 150 is. So when I do that, I get negative root 3 over 2. And I'll want to rationalize, or get rid of this complex fraction thing going on here. So to do that, I'm going to multiply the top and bottom by 2. But I can't just do 2 over 2 like that, because all of this stuff is underneath a square root. So to multiply it into that square root, I need to have a square root around this part. So when I do that, the 2's multiply in. So I have 2 minus root 3 over 4. And if I look, the denominator, I can take the square root of 4. So I'm going to go ahead and separate my radical so that I can square root the denominator. And that'll be my final answer. Any questions on what I did there? Okay, let's do one more, just to make sure. So let's say we want to do cotangent of negative 105. So the first thing I'll notice is that I don't have a half angle identity for cotangent, but I know that cotangent is the same as 1 over tangent, and I do have a half angle identity for that. But the tricky thing is, for tangents, I have 3 choices. I would certainly pick one of the ones without the plus or minus and the square root, since I have choice. One of the bottom 2 is going to be easier to deal with. And personally, I would pick this one, because when we take the reciprocal of it, since I have 1 over tangent, I'll have just the sine u in the denominator rather than the 1 plus cosine u. So if I have to rationalize the denominator, that'll make life much easier if I don't have addition and subtraction in my denominator. So this is going to become 1 plus cosine of negative 105 over sine of negative 105. Notice that I did the reciprocal of this one because I have 1 over tangent. Right, everybody can kind of see that? Okay. Oh my goodness. Guys and girls. I made a boo-boo ouchie here. So really I want to write this as negative 210 over 2. Because when I do the half angle formula, these need to be 210s. Or negative 210s. Ay caramba. Easy mistake to make, I just did it. So we got to be careful about that, right? You get going too fast and you forget to do the simple thing where you have to take negative 105 and write it as something over 2. Jeepers creepers, Mr. Gulick. Sorry guys, I made a mistake. Okay. So negative 210 isn't exactly a value on my unit circle, but if I add 360 to it, I can find an angle that's coterminal to it. And that is now a value on my unit circle. So if I go to my unit circle, the cosine of 150 is negative root 3 over 2, and the sine of 150 is 1/2. And then if I multiply the top and bottom by 2 over 2 to get rid of this fractions inside of fractions business, I get 2 minus root 3 over 1, or just 2 minus root 3. We might ask you to do some like identity proofs with this. So let's say we have this statement that we want to prove. So if I look at which side to work on, I would certainly pick the left-hand side because I see the half angle there staring at me. So I can use my half angle identity, square away. But notice that I have cosine squared of x over 2 and not just cosine of x over 2. But that's not a big deal, because all I'll do is put in my identity for cosine of x over 2 and just write the squared after it. Right? That's the same thing. Now that squared on the outside is tremendously helpful for us, right? Because I know that the squared is going to cancel the plus or minus, because plus times plus is positive and minus times minus is positive. And the squared is also going to cancel the square root for me. And I notice that when I multiply these, the 2's can cancel. Oops, forgot to copy the secant with it. And then I can rewrite cosine as like 1 over secant, or I could have written secant as 1 over cosine. It doesn't really matter. This way is going to be a little bit quicker, because when I distribute through, I get exactly what I need. And I don't have to take another step then transforming the 1 over cosines back into secants, but it'd be fine either way. Okay, we okay there? Cool. The last section is we're going to revisit proofs and solving. So we're just going to do some examples. This is basically the same ideas as things that we did in the previous chapter, just with the acknowledgement now that with the proofs we can do any of these half angle, double angle, power reducing, sum and difference. We can use whatever of those that we want. And the solving actually gets easier, because now we don't have to worry about like solving cosine of 2x and having to like write the infinite form. And then when we divide by the 2, we reduce the coterminal amount. We can just turn everything into x's before we use our inverse trig functions. And we don't ever have to worry about that ever again, which is really nice. So if you're not quite sure what I mean by that, I'll explain here when we do some examples, and it'll become should be a little bit more clear. But I'm going to start with a couple of proofs first. So first thing we would want to do is take a look and see if we can determine the side we'd want to work on. I would work on the left-hand side because I see the 2x there. It'll be much easier to turn that 2x into into x's. But I don't have either a sum of 2 angles, so I could write the 2x as x plus x, or I could write think of it as a double angle. But I don't have either one of those for a tangent or for a cotangent. But that's not a big deal, because the first thing I'll do is just rewrite this as a tangent using my reciprocal identity. And then now I have a choice to use the angle sum or the double angle, because I could write this again as x plus x, or I could use a double angle. I think the double angle one's going to be a little bit easier to use. So that's the one that I'm going to opt for. But it would be possible to do either. I think it's just going to be a little bit more convenient to do this one. So I have 1 over this, so basically I'm just going to make a reciprocal of that fraction. So the 2's can cancel. And then I'm just going to rewrite this as two separate fractions. So I can write as 1 over tan x minus tan over tan x. 1 over tan x is cotangent. And then the other one can reduce, so I'm left with just the tangent, which is exactly what I was looking for. So I'm done. Let's do another. And then after this, we'll do some solving examples. So here, again, I'll look at this and go, okay, probably want to work on the left-hand side because I see the 4x. I can use some angle sum or double angle identities to deal with this. I tried this with the angle sum in 4th hour, but I think it turns out it was going to be easier to use a double angle to do this. So that's what I'm going to do here. So I'm going to think about sine of 4x as 2 times 2x. So I can use my double angle. And if you remember back, there was 3 versions for the double angle formula for cosine. The one that I'm going to pick is the one that starts 1 minus. And since it's a double angle of 2x, the variable I'm getting is 2x. When I do this, everybody okay to hear? And now again, I could think about this as x plus x and use the angle sum for sine, or I can think of it as a double angle and use the double angle identity for sine. I'm going to use the double angle identity. So that is sine x times cosine x. Either would be fine. You'd end up getting the same thing. And then I still have this squared here, so that's going to go on the outside. And now when I square a product like this, I get 2 squared, sine squared, and cosine squared. And 2 times 4 is 8. And that is exactly what I was looking for. And I think that's the easiest way to do that one. I tried doing it with angle sums, at least to start, and it wasn't bad, but it definitely was more steps than this one was. But just to let you know that you certainly could have done it that way, and it would work out. It would have been fine. Let's do a solving example or two, and then we'll be done here for today. So we're going to solve on the interval 0 to 2 pi. Cosine 2x equals sine x. So what I would do here, like we've done in all of the previous problems, is start by getting everything onto one side. So I'm going to subtract the sine from both sides, and sine and cosine are not like terms, so they can't combine. We'll just kind of write the minus sign right next to it. And then I'm going to transform cosine 2x so that I have just x's. So I could either use the angle sum and think about that as cosine of x plus x, or I could use one of the double angle identities for cosine of 2x. That's the option that I'm going to take. It would be fine if you did the angle sum. No big deal. I'm going to use the double angle, though, because I think it's going to be a little bit easier. So, again, there's 3 options for the double angle. The one that I'm going to choose is the one that has only sines in it, because the other trig function I have sitting there is a sine. And now I have something that looks a little quadratic, right? Because I have a constant, I have something squared, and then I have something to the first. So I'm going to try to solve this like a quadratic. But before I do that, I'm going to go ahead and do a little bit of finagling here. So I'm going to divide everything by -1 so that my leading coefficient is positive. Because in my opinion, that just makes the solving or factoring that we're about to do just a little bit easier if I have a few less negative signs rattling around in there. So if you look at this, if we think about a as sine x, we're really just kind of solving this quadratic, right? And there's 2 good ways to solve a quadratic. We could try to solve this by factoring, or we could use the quadratic formula. Since the leading coefficient is 1, I can't use a lot of my easy factoring shortcuts. So I think what I'll do here is just use the quadratic formula, which is -b plus or minus the square root of b squared minus 4ac all over 2 times a. So -1 minus 3 over 4 is -1. And -1 plus 3 over 4 is 1/2. But we don't want to solve for a. We want to solve for sine x. So let's go ahead and plug those back in. So x is going to be sine inverse of -1. So if I go to my unit circle and look for the place where the y coordinate is -1, that happens at 3 pi over 2. And then the same idea over here. So that happens at pi over 6 and also at 5 pi over 6. So those are my answers. Notice at no point here when after I applied the inverse, did I have to divide by 2, right? We noticed in last chapter when we did that some funny things could happen, and we had to be very careful about making sure that we found all of the answers, because all of our answers weren't necessarily things on the unit circle. But here we don't have to worry about that because we eliminated that from the get-go. All right, let's do another one. and then we'll be done for today, at least with the notes portion. Okay. So just like before, I would start by moving everything onto one side. So I'm going to add cosine squared, or 2 cosine squared to both sides. And then I'm going to use one of my identities to get rid of the 2x here. So I can either use the sum of 2 angles for sine, or I can use the double angle identity. The double angle identity, I think, would be the better one to use here because it's got just one term to it instead of having another sum there. I think it'll probably just make life a little bit easier to use that one. Now I notice that everything has a factor of 2 in it, so I'm going to just divide both sides by 2 to get rid of those 2's. And then I'm going to factor. So I notice that I have a greatest common factor of cosine. So I can factor a cosine out. And now that I've made this a multiplication problem equal to 0, we can apply the zero product property to set each of these factors equal to 0. So here I get x's cosine inverse of 0. And if I go and I look at the unit circle at the places where the x coordinate is 0, that happens at pi over 2 and 3 pi over 2. But those aren't actually the answers that I want, because the answers I want need to be between negative pi over 4 and negative pi over 2. So all I'm going to do is find answers that are coterminal to these two. So I'll subtract 2 pi from each of them. And negative 1.5 pi and negative 1/2 pi are both too big. So I'll subtract another 2 pi. So 3.5, or negative 3.5 pi and negative 2.5 pi are both in the desired interval. So I'll circle those. And then we'll go back to this other one. So this was a trick that we saw in the previous chapter. When I have a sine plus a cosine, or a sine minus a cosine, or some combination like that, what I need to do is just create a tangent out of this. So I'm going to subtract sine from both sides, and then divide both sides by cosine, and then divide by a negative 1. So I can say that negative 1 is equal to tangent of x. So if I go to my unit circle and look for the places where y over x is equal to negative 1, that happens at 3 pi over 4, because I have root 2 over 2 divided by negative root 2 over 2. And it also happens at 7 pi over 4, because there I have negative root 2 over 2 divided by positive root 2 over 2. But again, these two are not in the interval that I'm looking for. They're not between negative 4 pi and negative 2 pi. So we'll do the same tricks. So I'll subtract 2 pi from each of these. Oops. Yeah. So I have negative 1.25 and negative 1/4. Again, still too big, so we'll just do it again. So this is negative, what is that? 3.25 And then this is -2 1/4. So those are both in between -2 and -4. So those are my answers. Any questions on these solvings? Again, this should feel, at least at the end, when we're actually coming up with the answers, a little bit easier to deal with than the things in the previous chapter. One, you're more familiar with the process, and two, we don't ever have to worry about, again, once we've gotten to like this point, having like a 2x or a 3x or something here that we have to be very careful about. We're just going to have x's, which is wonderful. It really makes life a lot easier to deal with. So as far as the homework goes, you should now be able to finish the problem set, and you should be able to finish worksheet 1. And we've done all the content here for chapter 6. So on Monday, all we'll do is kind of just take questions from homework. And that'll be all.